Okay. At the last lecture, I was talking a little bit about some of the chemical problems that occur with materials for making pipelines. And we were talking about hydrogen cracking and the effect that that would have, particularly on rolled steel plate. So you can tell this is a rolled steel plate because of the directionality of the microstructure, which is obvious in this etched surface. And we get non-metallic inclusions that line up along in the rolling direction. And these little cracks that join them up. Similarly, you could get cracks that run in a chevron arrangement, depending on where the residual stresses are. But in this particular case, we can see ones that line up in the rolling direction. And the point I draw your attention to, which is sometimes very obvious as to why these cracks form, is you get this flat crack, and then at the end, the cracks bend up and down. And they sometimes call them hook cracks because the crack, at the end of the long defect, the crack doesn't stay in the plane of rolling, it moves out of that plane. So you can see one here, one here. And that enables you to jump from one level to another. So this crack is attracted to this crack, and this crack is attracted to this crack. You can argue it that way around. And that's why you can link individual crack layers, and then the cracks get longer and longer and longer, and eventually catastrophic failure can occur. So sometimes the cracks look a bit like a ladder or a set of steps. So you get a crack here, going up here, going up here, going up here, and running along. But if you look at the detail, the end of the cracks tend to be a little bit bent over. So you don't want this to happen. So what do we do about it? Well, the first thing that we can do is we can limit the sulfur content of the steel. And desulfurization has become a common process in steels for these sorts of circumstances. We're trying to get the steel content down to a very low percentage in the parts per million level. And the standards for the material are written, and this is something you can analyse for with the steel, so you want to check that out quite nicely. We can calcium treat the steel. We can add a small amount of calcium metal into the molten steel in the blast furnace, and what that does is it changes the surface energy of the manganese sulfide in particular. So instead of ending up with long, thin plate-like inclusions, the inclusions remain round. So instead of getting a long, thin plate of the inclusion, you get lots of small, round droplets, spherical droplets. And spheres are much better than plates or laths of material. So again, a small amount of calcium in the steel, that's probably what it's been added for. Obviously, we want to reduce the hardenability of the steel, make it less susceptible to cracking, and that means keeping the carbon, manganese, and phosphorus as low as possible. Carbon and manganese, that if you looked at your weldability equations, they're obviously important contributors to that. Phosphorus is one of these impurities. It doesn't affect the hardenability, but it's another embrittling element that you want to reduce, like sulfur. Not quite as bad as sulfur, and a small quantity of phosphorus is good because it will increase the strength of the steel, but too much phosphorus and then you can get brittleness, so you want to avoid that. And hydrogen just makes all these things worse. So anything that makes a steel brittle, if it's in the presence of hydrogen, it will make it more brittle and much worse. We want to use the thermomechanically controlled processes, so controlled rolling, to reduce the grain size of the steel to improve its strength, because that improves its toughness as well. And if you can do that without adding alloying elements, then you will tend to get a microstructure which is much less susceptible to hydrogen cracking. Similarly, a quenched and tempered steel, where the microstructure isn't strengthened by large numbers of alloying elements, that will give you a much better resistance to hydrogen-induced cracking. And finally, if you are looking at what I would say is more the atmospheric corrosion. So if you're looking for acid rain resistance on the externals of pipelines or the external things, people will sometimes add copper to steel because that makes a very nice oxide that's protective on the outside. Best example of that I can give you around here is the Angel of the North, which is made of a core 10 copper containing steel and is not painted, because the weathering of the steel creates an oxide layer which protects the steel from further corrosion. If you think about steel rusting in the environment, you get brown rust, which you can wipe off with your finger. It's very weak, not very protective. But if you can get black rust, then that's actually quite protective. And that's sometimes the anti-stone chip treatments you use on your car turns the steel black. That's producing the black rust. So the black rust is Fe2O3, and that's protective. And brown rust is FeO, and that's not protective. So you want to form these Fe2O3 layers to actually give you very good protection overall. Adding copper to the steel makes it more likely that you form the Fe2O3 with a little bit of copper in it. So if you look at the Angel of the North, it looks slightly coppery in its colour because we have these copper oxides present in the surface as well. And that weathering steel is great, but it's only good for atmospheric levels, because if the pH gets too low, that surface is damaged. So when you have pipeline systems containing products that have large quantities of acid gas or large amounts of CO2 in, then it's probably not effective. But for long pipelines running across Canada, where you might have some atmospheric protection problems, where the paint systems can't stand the temperature cycling, then you might consider these sorts of steel. It's a question that you have to ask yourself as to what you need for the pipeline that you're designing. So, for corrosion problems, you've got the pipeline material itself, but you also have to worry about the weld. So, sulfide stress corrosion cracking has occurred here. We had a crack in the toe of the weld, which has gone in through the heat affected zone. So, in this particular case, there was a metal sulfide that had formed on the surface there, and the conditions underneath that sulfide became very acidic, and that caused the crack to run through. So, when you're looking at welded structures, you have to treat the welded regions differently to the rest, and they will sometimes have a small area compared to the large area of the rest of the pipe. So if there's a corrosion process which is more likely to happen that will dissolve away or that will attack the weld, it works on the small anode effect, that got this large inert pipe and the small area where the corrosion will be focused. And for that reason, you can sometimes get problems of corrosion with a galvanic cell, if you like, set up between the pipe itself and the weld, because they're not quite the same. So people who work in the marine environments know this. They always do a separate painting operation on top of the weld, and then they paint the whole system afterwards to make sure that you've got extra corrosion protection on the weld and weld region. They even do it, they paint it in a different colour to make sure that it's been done, so that you can see that it's there. So you have to think about that. So if we want to avoid these types of corrosion, again, if we use low carbon equivalent pipe and low carbon equivalent welding materials, the material is less susceptible to cracking, and therefore that's going to be an improved performance. We use preheat and reasonably high heat input when welding. This slows down the cooling rate and stops you getting brittle martensitic phases. It also drives off any moisture and things at the surface. So preheating is commonly specified when we're making field welds, where the environmental conditions are such that you might generate extra hydrogen. Keep the hardness low. You can check the hardness. There are the portable hardness testers about the size of a cigarette packet that you can put on the surface, and a little indenter will be sprung load into the surface and will come back and you can measure that. If we keep the hardness less than 22 Rockwell C, there's 248 Vickers hardness, generally there isn't a problem. And that means you're unlikely to have formed any of these high hardness martensitic phases, for instance. If that shows up a problem, you might need to do a post-weld heat treatment. You ought to avoid that if possible, because heating a pipe to 600 degrees C for an hour, if it's less than 25 mil of thickness, is quite a difficult process. It can be done. A mixture of heating tapes and oxyacetylene torches can get you to those sorts of temperatures, but it's time consuming, it's expensive. It's to deal with disasters really, rather than as a routine process. So if you can control the heat input during the welding process so you don't get the structures in the first place, it's better than dealing with them afterwards. So for sour service, so we're talking about H2S containing systems. We have low carbon equivalent clean steels with not many inclusions in them. A clean steel means the inclusions have been reduced. You can put a cyclone, a bit like a Dyson vacuum cleaner, in the melt, and you could get rid of some of these particles for doing that by simply the fact that they are lower density than the metal. So we have these modern clean steels with low carbon equivalent, and in UOE pipes, which we'll talk about later on the manufacturing route, up to grades X60, X65, that's probably good enough. So with a corrosion allowance and of slightly extra thickness therefore, and a good quality steel and a well-controlled welding process, you probably don't have too much of an issue. But if you're going to these higher grades of steel, then we need to think about what you're going to do. So one of the problems I mentioned was a problem with welds. So reduce the number of welds is a way if you've got a problem with sour service, so seamless pipes become more attractive under those circumstances. Generally, seamless pipe materials have a slightly higher carbon equivalent and a slightly higher sulfur content, but even so, because of the way that they're manufactured, because they don't use this roll plate, it's a quenched and tempered material, generally the inclusions are round, they're not pancake or flat, and so they have better performance. Now, so why don't we use seamless pipes for everything? As we'll see later on, that they're much more difficult to make reliably. And high-frequency welded pipes, again, you can have reasonably good properties, but you need to take care. And again, it's down to the original steel strip that's used for making the pipes. It needs to be clean. It needs to have good quality provision so that it's reliable. And you need to make sure you've got proper heat treatment of the seam weld once you've made it to ensure that it has good properties. What you don't want is the properties of the weld region to be very different from the properties of the rest of the pipe, because then you get a galvanic cell set up between them and you'll get corrosion generally in the weld area, and you want to avoid that if at all possible. So generally that's where we are, and even up for X80 pipelines in this country, we're not using anything unusual. But there comes a time, often at the wellhead and sometimes in processing facilities, where the environment is so aggressive that even the best carbon steel pipe can't be used. So what do we do then? What do we do? Well, step number one is go for a corrosion-resistant steel. And so somebody will say, oh, let's use stainless steel. Now that is a bit of a hostage to fortune statement, because the question that should come back then is which stainless steel? And stainless steel is not a single thing. And so what I'm going to introduce to you in the next few minutes is the different types of stainless steel, and I'm going to highlight the ones that you're likely to see. They're all good corrosion resistant steels, but some of them are not suitable for applications in pipelines. So what is a stainless steel? Well, it's an iron-based alloy, so it's like the carbon steel that we talked about, except there is more than 10% chromium added. 10%-ish, could be 8 or 9% in some particular compositions. And there are 4 main types of stainless steel: ferritic, austenitic, martensitic, and duplex, which is a mixture of ferritic and austenitic components. So you can see they're all based on the main phases that are present in the phase diagram and can be produced by rapid cooling. Now, when we talk about stainless steel, if you say go to B&Q, the local hardware store, and say, I want some stainless steel, chances are it'll be an austenitic stainless steel. That's the corrosion-resistant one that most things are made from. And it'll probably be 304 stainless steel. So when people say make it out of stainless, that's generally what they mean. But you could pick all of these other options. So you need to be a bit careful about which ones you actually get. Stainless steels are not stainless if you put the wrong steel in the wrong environment. This is just a piece of cutlery. It's a table knife. It's actually a ferritic stainless steel in this particular case, and it's been in a dishwasher. And then my daughter tried to eat her dinner with it and managed to crack the end of the knife just by pushing on the plate. So what that tells you is that stainless steel is not stainless if it's chosen in the wrong environment. And chlorides can cause pitting corrosion, and they can also cause these sort of stress corrosion damage if you're not careful. Unfortunately, anything offshore, chlorides are very, very common. And in fact, in a lot of onshore applications, these are common. And sometimes people think they can use, for instance, they can use seawater in heat exchangers, in welded stainless steel constructions, and are surprised when the whole thing perforates in 6 months because of localized corrosion, because they got the wrong steel. So you need to be a bit careful. So we start off with martensitic stainless steels. These are just your low carbon steel with about 12 to 16% chromium. And they're used for cutlery and sharp tools. Now, chromium stabilizes the body center cubic alpha ion form of steel at the low temperatures. So you might think that makes it better. But unfortunately, if you've got only 16% chromium, you still will transform to austenite on heating, and you will, if the cooling is quick, transform to martensite. And that's why they're martensitic steels. They form martensite. Because at 12 to 16% chromium, the carbon equivalent is very high, and the ease of forming martensite is very, very good. So basically, you heat them up, and when you weld them, they form martensite, and it's almost impossible to stop. So these steels sometimes have nickel and molybdenum, as well as the iron and chromium. They have high strength, they've got good chloride stress corrosion cracking resistance, moderate general corrosion resistance. So you might say, well, these could be okay, but they're martensitic, so they're very brittle, and that is a problem. So typically, you have weldable steels that have chromium towards the lower end of that range, mostly about 13% chromium. And you can see the yield stresses here are very high. This is equivalent to X65 or thereabouts. So you can have quite good performance, but they crack. So maybe not the best choice. You can weld them, but you have to preheat to 200 to 300 degrees C. And post-heat to about 700 degrees C, and then post-heat to remove all the martensite. As a welder, with a torch, going in to weld something at 300 degrees C is not nice. I can tell you from bitter experience, it's not something you want to do unless you actually have to. And it involves extra skill at being able to weld in that hot environment. You have to have heat protection as well as your normal welding gloves and things. So it's much more difficult to weld. Your hands have got these larger gloves and things on, and it's well, I don't think it's something that I would want anybody to do, but it can be done if it's essential. You can use filler materials with similar composition, but they don't give good results. So generally we use austenitic stainless steel or nickel alloy fillers. So the welding consumable is expensive. Now, that isn't to say that martensitic stainless steel hasn't been used, but when it has been used, particularly in some of the downhole tubular constructions, it's often been with flanges and bolts to hold it together, rather than with welds. So in bolted joints, with an appropriate gasket between it, for very high CO2 environments, so largely in the sweet environments, there has been some use in the offshore industry of martensitic stainless steels. And I put this thing here, weldable grades are under development. I've been saying that for more than 10 years, and they're still under development. So part of the reason it's not more widely used is there isn't a good weldable grade. They're getting better all the time, and every year I see a new development and somebody says it's going to solve all the problems, but then it disappears quite quietly. So it's never quite as good as they hoped it was going to be. And it's largely because of the need, because of the very high carbon equivalent of the steels, the need to have all these pre and post weld heat treatments. You can make them the pre-treatments not so aggressive, but they're still pretty bad compared to the plain carbon steel. If we add a bit more chromium to the steel, we get a ferritic stainless steel. So these have got 16 to 30% chromium. Now chromium's more expensive than iron, so the more alloying elements you add, the more expensive the steel's going to be. And this is quite an expensive steel because of the amount of chromium. Chromium, as I said before, stabilises ferrite at low temperatures. And the advantage with this amount of chromium is you don't get transformation to austenite on heating. You keep that ferrite structure up until it melts. They remain ferritic, and if they remain ferritic and don't get the transformation to austenite, then they can't form martensite when cooled. So they can't form brittle phases on cooling. Except they just form different brittle phases. They form what are called intermetallic phases. Reactions between chromium and iron to give you phases. So, but it's different, and it's not as bad as you would get with a martensitic steel. They have good strength, good chloride stress corrosion, cracking resistance, good corrosion resistance. They have moderate weldability, as I say, because you can still form these brittle phases. They're not martensite, so they're not as bad as that, but there are intermetallics that can be formed. And in general, when you form an intermetallic, and that's when you've got a large proportion of these alloying elements, intermetallics pretty much uniformly are brittle. So if you're going to get a reaction product, chromium iron as a separate phase, then you're going to have problems with weldability. So they don't harden when welded, at least not very much, but they do form these very small regions of intermetallics if you're not careful. They do suffer from excessive grain growth when heated to 950 or 1,000 degrees C. So what that means is in the welding process is that at the high temperatures when you're welding, the material the grains are getting bigger and bigger and bigger, and they're getting softer and softer and softer while you're doing it. So you can lose the mechanical properties by welding, certainly in the heat affected zone. In order to avoid this, you have to preheat to 50 to 250 degrees C, which reduces that cooling rate and smears out some of the differences in properties. Now, I said these materials are more brittle and they have these intermetallic phases in it. The way that you see that is the ductile to brittle transition temperature is much, much higher than with the other systems. So you can actually have a ductile brittle transition temperature which is above room temperature. And if you, in some cases, it can be as much as 100 degrees C, so it's brittle at room temperature and it's ductile at 100 degrees C. Now that means when you cool down from welding, it remains ductile at high temperatures, it goes through a brittle transition, and just at the end of the welding process, just when it's cooling down, it cracks at the end of the process. So we maintain the temperature of preheat, so we're above comfortably the ductile brittle transition temperature, and that allows us to get down to room temperature without cracking. It also allows us to anneal the residual stress which would cause that cracking in the first place. This is a big problem, and it's an inherent problem with the material because of this ductile brittle transition temperature, and for that reason, if alone, you wouldn't really want to use these materials. And in fact, I am not aware of any use of ferritic stainless steels in pipelines. Occasional bits in chemical plant, but not really in pipelines. So everything leads to austenitic stainless steels. That is the stainless steel. All the ferritic stainless steels, you can tell they are ferritic because if you put a magnet on them, it will stick. They are ferromagnetic. So anything with ferrite in it and martensite is magnetic. Austenitic steels are non-magnetic. So in order to make the steel austenitic, we need to stabilise the face-centred cubic austenite structure, and you add a face-centred cubic metal like nickel in to counteract the effects of the chromium, which stabilises the body-centred cubic ferrite. So nearly all austenitic stainless steels, I'll rephrase that, all commercial austenitic stainless steels contain nickel and chromium, and it's about 8 or 9% nickel necessary to stabilise about twice the amount of chromium. Nearly all of the commercial grades also have other elements added. Molybdenum is an example. Molybdenum is added to increase the resistance to corrosion, particularly to pitting corrosion in chloride environments. So 304 stainless steel, which is the common stainless steel, has 18% chromium and 8% nickel. 316 stainless steel, which is used in medical and chemical applications, has 4% molybdenum added to that 304. So you can already see that just in the same material, you can have different grades which are suitable for different applications. And there are stabilised and unstabilised versions of these steels, which may or may not have a percent of titanium or niobium added to them. And again, that depends upon whether you want the steel to be weldable or not. So there's a whole range of things you have to consider. But if we look at it just in general terms to start off with, good general corrosion resistance, good toughness, good weldability, lots of alloying elements, therefore expensive. That's the main difficulty. And the one that kills it for a lot of applications is low strength. So you've got everything you want, but you've achieved a good toughness by having nothing that can increase the hardness and strength of the material left in the system. So for every chemical plant, every food processing facility, and some pipelines, you will use this type of material. The low pressure pipelines, you can use this type of material. And the ones that are usually specified for use in the chemical industry, and that includes in pipelines, are in this table here. So 316, which is the molybdenum, you can see 2.5% in this case here, chromium and nickel, slightly more nickel than I was talking about with the basic 304, because you've had to compensate for the molybdenum with a bit more nickel. Has a very low yield stress, 170 megapascals. That would be about X20 if you wanted to do it. It's really quite low. But you can go to these higher grades here, and you see that they've started adding other elements. and the strengths go up. The pitting resistance equivalent number is a way of sort of taking those alloying elements together and seeing how resistant they are to these pitting reactions. And you can see chromium helps, the higher the number the better, molybdenum helps, and nitrogen additions help, which is why these ones here have got nitrogen additions. So the whole idea is that you optimise your steel by finding the things that do what you want and adding them in quantities that don't have a bad effect. And then people have improved steels. The austenitic steels that are commonly used are these ones in the middle here, because their strength is probably up to somewhere in the region of X42. In that sort of case, maybe a little bit lower, but they are within the range of what might be used in the industry. That means that if you want to use them, they tend to be thicker because they have to withstand the same pressures. And if they're thicker, you're buying more material, and if you're buying more material, they're even more expensive. So that's the reason why we try to avoid austenitic stainless steels unless we have to. But they are very widely used in industry, and there are good quality supplies available. So welding austenitic stainless steel is relatively straightforward. They don't harden on welding. It has a low thermal conductivity. Stainless steel has surprisingly low thermal conductivity. And that means the heat affected zone is narrow. They also have quite high thermal expansion coefficients, and this means we can get solidification cracking. So you deposit your weld metal at high temperatures, and the parent metal expands away, and it pulls the weld metal apart before it's solidified. So you get a crack right down the middle of the weld. And if you don't actually clamp everything together properly, you can get that happening. There are plenty of good quality filler rods available. Low strength is the limitation. There's not a lot of offshore use. Process pipe work in chloride environments, water circuits and gas circuits on rigs, for instance, are sometimes made in these materials because they're low pressure systems. Where we've gone, though, is we've tried to get the benefits from the ferritic stainless steel, the high strengths and things, and the benefits from the austenitic steels, the weldability and the good toughness. So why not have a steel which has got both of these phases present within it? Can we optimise that? And that was the invention of a very useful class of materials called duplex stainless steels. Now, you could have an entire course on duplex stainless steels, so there's an enormous amount to say, but I'm going to cover it very, very basically. So they're designed generally to make a mixture of 50% ferrite and 50% austenite. So we reduce the amount of nickel in the system, and we slightly increase the amount of chromium compared to the austenitic steels. And these materials have very good stress corrosion cracking resistance. They have very high strength. They generally have good toughness if you process them correctly. Good general corrosion resistance. And if you've got a high pressure application in a corrosive environment and it's not too corrosive, this is your material of choice. So they're used a lot in chemical plants and pipelines in high pressure applications. And if you're into renewable energy and you've got a solar water heater and you go and buy a water tank, you won't have a copper tank because these tend to operate at a higher temperature, a higher pressure. You'll have a duplex stainless steel water tank in your house. So, you know, there are quite a lot of common applications of this type of material. So we have the duplex steels, and you get different suppliers. SAF 2205 is very, very common. That's the basic duplex steel. And then people have worked on improving that by adding a little bit of copper, increasing the amount of nitrogen, because we can get better pitting resistance equivalent numbers, so we can get better. So we go from duplex to super duplex. And super duplex as its name implies, is better than the previous one. It's just a way of pointing that out. Now, what I would say is as you go from duplex to super duplex, the alloying element content goes up. So, what I've been saying, higher cost. Everything comes down to cost in these cases. Going from a duplex to a super duplex might add, on a long pipe run, £100,000 onto the price of your job. So you've got to want that. You've got to be able to recover that extra price. Duplex might be okay. You might even say, well, we'll have a clad pipe or something which is cheaper to make. You have to be careful. So we can weld them, but they have to be welded with special rods. A huge amount of effort was put into developing welding techniques for super duplex and duplex steels. And the advantage about this is that effort paid off, and there are good ways of welding them now, unlike the weldable ferritic grades, which we never really achieved at the weldable martensitic grades. So what you want to do is you want to ensure that the best composition for corrosion resistance, which is this 50-50 austenite ferrite mix, is maintained in the welding. So that means you tend to have to use a higher nickel content welding consumable than you do in the manufacture of the pipe material itself. And that means the final composition will be correct because there's dilution effects. The welding consumable dissolves into the weld pool and mixes with the parent metals. And you want to maintain that 50-50 composition range. You have to avoid low heat input welding, so not too little heat. And you want to control the maximum interpass temperature, so you don't want it to get too hot. So there's a range, there's a narrow range of acceptable welding conditions. And hot cracking can occur if you put too much heat in, so that's controlling the amount of heat that you want to put in. Saying that, it's all about control. It's not impossible to weld duplex steels. It's quite straightforward if you've got the right level of control in your process. And that's why they're widely used for pipelines. Generally, that short distance from the wellhead to the first processing step, or the first distribution step, where you get high pressure, highly corrosive systems before you've dropped the pressure down for transport, that's where you would put these types of materials. Now that's all very complicated, and how do we draw this all together? If I'm given a particular steel, how do I know which one it actually is if I've got the composition? Well, there's this thing called the Schaeffler diagram after Professor Schaeffler. Everybody likes to have their name on these things, which plots nickel equivalent, so these are the austenite forming elements, against chromium equivalent ferrite forming elements. And then we can plot on this diagram the regions that correspond to the different phases that you'll form, and the regions therefore which point out which steel we actually have. So the chromium equivalent is chromium plus molybdenum plus 1.5 times silicon plus 0.5 times niobium. So obviously we go from a carbon steel here to a martensitic steel here as we increase the amount of chromium, to a ferritic steel when we get very high. So we've got a region for ferrite, a region for martensite, and then mixed regions, martensite plus ferrite, or ferrite plus martensite. If we go in this direction, so we pick the chromium content here, we've got a ferritic steel, and we add more nickel, we start to stabilise the austenite, and eventually we get into a fully austenite stabilised region here. So, if you have a martensitic steel, it will be around here somewhere, in this region. If you have a ferritic steel, it'll be here. If you have an austenitic steel, it'll be here. And duplex steel, this is the austenite plus ferrite, 50% is somewhere around here. So you should be on a line somewhere here. So if you're given the steel composition, you should be able to plot it on this diagram and work out what type of steel it is. That's sometimes quite necessary, because sometimes the supplier will send you a steel and claim that it's martensitic, and it turns out to be ferritic. Because it meets the strength requirements, you're being delivered against a mechanical specification, doesn't mean that it's delivered against the chemical specification, and you may need to check. What this plot also shows is the failure modes that you might actually get. So the horizontal lines here, in the austenitic region, that's solidification cracking, or ductility dip cracking above 1250 degrees C, high temperature cracking, which is a feature of austenitic steels. So the vertical ones here, ferritic steels, show temporary embrittlement at 475. If you heat something at 475 degrees C for a long time, you can embrittle the material by forming these intermetallics. In the duplex steels, we get another phase formation, a sigma phase formation, and that leads to embrittlement, again, heating at 500 to 900 degrees C. So you can start to see where different failure modes occur associated to the different types of steel on a diagram like this. Most useful for identifying an unknown steel and then working out what you're going to do with it. The last thing you need to know about with stainless steels really is the fact that they can degrade. And there's a thing called weld decay, which occurs very commonly in what we call unstabilized stainless steels. So what happens is you make the weld, put it in a corrosive environment, and after a period of time you start getting excess corrosion in the heat affected zone, some way away from the weld. And it looks like the weld is rotting, weld is decaying. That's why we call it weld decay. And you can see here is a decay region. These are the individual grains. You can see the grain boundaries are quite tight here, but they're really open here. What's happened is the corrosive environment has just corroded away the grain boundary material, and it falls out. And you get very big corrosion pits, very rapid corrosion. And what's happened is, during the welding process, the chromium that you add to make the steel corrosion resistant reacts with carbon that's in the steel, particularly in the grain boundaries, to form chromium carbide. And when it forms chromium carbide, it can't form a protective chromium oxide layer on the outside, so the ends of the grain boundaries tend to be open to attack. And that then means that you just dissolve away the grain boundaries, and the grains fall out, and that's what weld decay actually is. So you've got to do something about the carbon that's in the steel. Stainless steels don't have much carbon, but there is a bit, and you have to manage that carbon. So you can do hydrogen treatments to reduce the carbon, very expensive, or you can add other alloying elements to so-called stabilize the steel against this type of attack. If you add something that forms carbon more likely than chromium, that will do it. So we add a bit of titanium or a bit of niobium to stabilize the steel, and then that ties up the carbon, and the chromium's available for corrosion protection after that. Just to give you an indication what effect the carbon content has. So this is the time to form harmful amounts of carbides, and the time at temperature here, and the carbon contents. So if we have 0.8% carbon, a cutting tool type composition, you form harmful amounts of carbides in about 15 or 20 seconds at those temperatures. You can achieve that on cooling down from the high temperatures. Generally, if a welding process and the cooling process in a weld is controlled, we want something which will be able to cool over about an hour. That's not an unusual cooling time. So if we do that, harmful amounts of carbide forming in an hour, we have to get the carbon content down to 0.042% in the steel. That's expensive to do, unless you start adding these alloying elements. So we physically can't reduce the carbon content low enough by cost-effective processing. Best solution, therefore, is to use alloying elements in those cases. Right. What happens if you have a material that has to go in a very, very aggressive environment, very high content of sulfur, let's say. Well, then you go to another alloy system. You replace the iron in your alloy with nickel. And there are two alloys, Inconel and Incalloy, which are commonly used for the most aggressive corrosion surface. They're nickel-based alloys. They can be welded, but they are very, very expensive. I mean, these are the sort of alloys that are similar to what you make gas turbines out of. And, you know, you have to really want to use these alloys if you can do it. Certainly on a pipeline, they're not really economically viable. But you can use a layer of this nickel alloy on the inside of a pipe or on the inside of a valve as a clad material or as a liner. And so 2 or 3 millimeter sheet of the nickel alloy can be put inside the pipe to actually give you performance that you need. So these are the sort of alloys. The strength, alloy 400, which is effectively pure nickel, is not very strong, but all of these alloys, 825 and 625 are the common ones. That's okay. Alloy C276 is sometimes known as Hastelloy, and you will sometimes see that as the bodies for pumps and things. It's a casting alloy. It can be used for cladding, but it's sometimes more in fittings that you'll encounter that. Not quite so good properties, but not that bad either. So they're better than austenitic stainless steels, but they're not as good as duplex steels in terms of strength. But they're very much more corrosion resistant. You can put, you know, boiling sulfuric acid into these materials, and it won't go through. So finally, how do we know which one to choose? Well, here's partial pressure of H2S on the bottom and partial pressure of CO2 on the vertical axis. So if you've got an analysis of the product coming out of your well, you should know what those are. If they're both low, standard carbon steel. As we increase the amount of H2S, you might have to have the modified carbon steel, calcium treated, whatever, specially designed carbon steels. And eventually you're into the nickel alloys here. As we increase the amount of CO2, that's when you tend to choose the stainless steels in the system. And again, duplex, super duplex, going up towards the more corrosion resistant corner. If you're up in this corner, it's nickel alloy or nothing. And that's why you want to choose the other things. So with selection charts like this, you can just go to it, pick where you are, pick the right materials, and then decide how you're going to make them into the pipeline systems. You also have to bear in mind that temperature affects things. So this is alloy 825, again CO2 and H2S, but the vertical axis is temperature. In this case, the stability of the material, the corrosion rate of the material increases as the temperature increases. So when you've got high temperature materials, you're pushed towards using these more expensive nickel alloys. And finally, for today, I don't want you to think that you'll use a solid nickel alloy pipe. I know of no examples where people use that for anything other than very small components, chambers and things. But clad pipe, where a mechanical bond of a thin film of the corrosion-resistant alloy on the outside, you'll have the carbon steel. That is widely used. And you can also well deposit the corrosion-resistant material inside the pipe if the pipe diameter is large enough. And again, that's cheaper than buying the full pipe. That's usually done for fittings, for valves and things like that, because the direction of travel and the time it takes to actually do the coating is very low. For long joints, you usually use these sheet manufacturing methods. And the problem is that you have to then seam weld a corrosion-resistant alloy. So you'll have a different welding process on the inside and on the outside of the pipe, and it just makes things a bit more complicated. And I'm going to finish there for today. This is an indicator of what we're going to be talking about next, which is how we make pipes. And so the pipe manufacturing process is quite critical. And there are different ways of making the pipe depending on the materials that you're of construction, and they are related in terms of how you're trying to achieve the end product. So you have to get the right material, the right manufacturing route for the right end product, and that's what's important about most materials. Okay.